Welcome to class meeting 16 of the Introduction to Optimization. Since this is a kind of makeup class on the same day as the previous class meeting, I'm not going to spend any time for the review, for the announcement. So let me start by reviewing what we learned last time. The problem was like this. Here is a model function. Of course, in this class, we have a vector-valued function of the parameter to be determined. However, in many cases, especially for statistical signal processing, we have a function of the observation and parameter, where we often use theta instead of x, but anyway, doesn't matter. This is parameter to be estimated. And our model says that in the ideal case, the model function evaluated at our optimal parameter equals 0 vector. However, this is not true in realistic case. For any x, the function is non-zero. So what we do is to minimize the norm square of the model function over the parameter x. So this is the problem of least squares. So this minimize corresponds to least, and this becomes squares. Okay? So least squares. Especially when m of x can be put in this form, ax minus b, then we call the problem of minimizing 1/2 ax minus b squared as linear least squares problem. So in general, we may have non-linear least squares problem. Now, among the linear least squares problems, we are interested in a little bit smaller set of the linear least squares problems, where the A matrix is a square or tall, okay, square or tall matrix A, and the vector B is a member of the span of the columns of the square or tall matrix A, that is same as the column space of matrix A. Sorry, not. What does this mean? What does this mean? These two conditions. This means for any x, ax cannot be b. But this also implies A transpose A is invertible. And obviously this is positive definite, so let me just say A transpose A is positive definite. Is it true? Something's missing, right? Yeah, one is missing. So rank of A equals n. Yeah. So the second condition says this. And first and third condition says A transpose A is positive definite. Now, this is a kind of intermediate implication, but the final implication of these three conditions is that we can just solve this quadratic minimization problem and get Gramian of A matrix inverse times A transpose B is the optimal solution that is unique. Of course, AX star is not B. So AX star minus B is not 0. And here, for the derivation of this one, you just need algebraic operations, manipulations. But to make a geometric interpretation, we define B star, that is A transpose, AX star, then we have what? A times A transpose A inverse times A times B. And here, this is nothing but the projection matrix to the subspace spanned by the columns of A. So if we draw, this is the famous figure used again and again. So this is the range of A, and let's say this is the origin. Then you have vector B here, not on the this space, subspace corresponding to the range of A. So you want to find some point here that is called B star, that is on this subspace and has the minimum distance. And minimum distance means that if you draw a hypersphere with a center B, then the distance from the point B to the to any point here is minimized when your hypersphere touches this subspace. Means that you have orthogonality here. So B minus B star must be perpendicular to this B star. And this is called the orthogonality principle. By the way, your solution can also be obtained from the orthogonality principle. That will be used again and again in the course of next semester, estimation and detection theory. Okay, yeah, that should be transpose here. You are right. And we examined some examples where I will talk talk again about this linear prediction part. So suppose, example 2. So this is example 2 of the previous lecture. Suppose we have made observations indexed by k, scalar observations, 50 of them. And here, this is y1, and here, this is y2, y3, something like this. Oops. Now, given that, consider this kind of case. Suppose you want to design an active noise canceller. Suppose you want to design an active noise canceller based on this training period. For example, what you need to do is that from here to here, you observe the random process, and based on these 50 samples, you are going to build a noise canceller that will be used to cancel the future values. Got it? So the story is like this. Here goes the sequence. Let me say case sequence. And what you do is that here you design a linear predictor. That uses P past values. So you want to use yk minus 1, yk minus 2, dot dot dot, yk minus p for some finite p. Now, linear predictor means that its output is some a1 yk minus 1, a2 yk minus 2, and ap yk minus p. Now, your objective is that this is what is this? Yk, right? And this is what? This is the prediction of yk based on past p values of y. So this is the error. Does it make sense? Suppose your system has very high computation power, so that your system can utilize just previous, up to just previous value. If you need you need some time to compute this one, probably your linear predictor may use yk minus 100, yk minus 101, and yk minus 100 minus p, something like that. And then, again, still this is y sub k hat. So, for example, you need some computation time. And you subtract. Of course, in that case, your error may be very large. But these days, computation power goes up and up. So, this may not be a that bad simplification. Suppose just single step is okay in this problem. Now, what would be the best case? This estimation error is minimized. Am I right? Now, how many such estimation errors can you make from this observation? When you have P, order P linear predictor. So the story is like this. Suppose your P is 2. Then you want to use y1 and y2 to predict y3. So you have two coefficients to find, and you combine y1 and y2 to predict the next value. Am I right? Now, what is the linear prediction of y4? Now you use y3 and y2, but with the same coefficient. So you have a1, y3, a2, y2, something like that, and up to y50. Now, you know that this is never y3. You will have some error. Anyway, any digital system has an error when it processes real-world signal. First, you have to convert it to a finite resolution some value. Quantization noise is inevitable anytime, right? And also, there are many other noise terms. So, ideally, you want to remove this hat. In that case, what is your model function? So let's say this is x, the parameter vector. Then what? You can choose A as y2, y3, and b1 is y3, y3, y2, y4, dot, 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 y49, 48, sorry, this is y50. And in the ideal case, this is 0. Am I right? Let me see. Yeah, y1. Am I right? And also, in this case, it is justifiable that minimizing this value, this vector, is a good criteria. Because what is this? This is simply the error vector. Y3 hat minus error vector. Y3, no, it's error vector, correct. Yeah. Y50 hat minus Y50. Am I right? Got it? So the least squares problem in this case exactly becomes the minimization of the prediction error. So anyway, you are going to, you start your noise canceller and you assume that it is some, you cannot, how to say it, simply classify that this is some Gaussian noise, this is something. But suppose your noise has some mechanism behind that, this fitting may work well. In many cases, there existed some important problem. So using these 50 samples, you find least squares estimate of A1 and A2. Then what are you going to do? From here, you just use this linear prediction to cancel the noise. For example, here you tap and connect it to active some actuator. It may generate counter vibration or counter acoustic signal so that your noise is cancelled. Maybe possible. But this is, too simple problem. Actually, a more realistic problem is more complicated than this. But anyway, I believe you get enough flavor of why this makes sense. Got it? Now, let's take a look at the example 1, example 3. That is the first example in our lecture note. Sorry. That is the second example in our lecture note. The first one was linear line fitting. So again, now the difference is that you are given a vector B. And what you want to do is that you want to approximate this vector using capital N vectors like this. x1 times s1, x2 times s2, sn times xn times sn, where these s vectors are pre-specified, so given to you, and these x values are to be found. So it's like, given a vector valued signal, you want to find a representation. So does it look similar to what you already have seen? Yes. For example, suppose you want to approximate a continuous and differentiable function using polynomials up to order 3. Then what do? Assuming it's differentiable 3 times, and also you approximate around x equals x0, then you have something like this. They look very similar, right? So using x minus x0 and x minus 0 squared and x minus s cubed, you find coefficients. This is to the zeros, order 1, 2, 3, right? Similar to that. So this type of, this is what? This is Taylor series representation of f of x up to order 3. A kind of simplified version for a vector valued signal would be something like this. Given pre-specified vectors, you want to find coefficients for the linear combination. But as you see here, this representation may not be exact. So I say this is approximately equal to. Now, what is our model function? In this case, it's too simple. We put all x's into the parameter vector x. Then this right hand side is nothing but S1 to Sn. So if you multiply capital A defined in this way times x, you have the right hand side. Now B is already given. And ideally, this is equal, so you may choose this A and this x and this B as those A, x, and B in the least squares problem. Now, the important thing is that whether that ax minus b norm squared is an acceptable cost function. As I told you, you can choose any model function given your problem. You can somehow change this to some nonlinear mapping, I don't know how, and claim that, okay, this is my nonlinear least square problem. But in many cases, this type of representation makes sense. You may say something like this. Okay, let's say that this is M. So you have 1, 2, 3, and M. So this is your B1, this is your B2, and this is your BM. Now, this is what? This is B hat, right? Then you have some vector that can be represented with these n dots. Is it n? Yeah, m dots. Then minimizing the square distance may make sense. For example, suppose your original real world situation is like this. Actually, your B should be this one, but unfortunately you have some IID noise. Independent and identically distributed noise. So you observe this B. Noise corrupted B. In that case, under certain conditions, you can show that this minimizing the distance is really the optimal criterion. So as far as, anyway, I'm not going to repeat all the derivations. As far as you have A, X, and B properly chosen, you are done with the least squares problem. Now let me move to recursive least squares. Recursive least squares is related to the noise canceller problem, the simplified noise canceller problem. Actually, noise cancelling is not that simple. I remember some undergraduate students try to build noise cancellers for their senior design projects, and most of them failed. Okay, it was not that easy. But anyway, let's continue continue to use that as our motivation. I have told you like this. So this is the observation index K. And you make observation from some starting point. Let's say that this index is 1, 2. And you use, for example, in the previous case, you use 50 samples for your training, and then use the coefficient A1 and A2 throughout the, for example, until you turn this system off. Okay? That was the idea. But does it make sense? For example, you start your engine of your automobile, and usually your car is parked in the parking lot, and no load is connected to your engine. Now you change the gear, or you change the gear to drive. then you also push the accelerator. And that will give you different revolutions per minute for your engine. Suppose that this 50 time indexes were just at the time you ignite your engine. Will this noise canceller work well? Definitely not. And also, you will say that, okay, suppose I am here at the time index 100. Now, these 100 observations are given, but you only used 50 of them. Does it make sense? Probably not. So, you want to somehow utilize this observations continually. By the way, given some possibly semi-infinite observation, suppose you use some of them and then use it again and again. That is sometimes called, is it correct? No, probably not. Batch processing. But anyway, let's modify that idea. Now, the question is like this. So, at each time index k, you have, let's say, a k, which have what? Y, was it 3, 2, 1, right? 2, 1, up to y k minus 1, y k minus 2. And let's define bk that contains y3 to yk. Am I right? As you remember. Fortunately, in this case, the size of x is just 2. So you may say that, okay, at every update of the data, I'm going to compute the projection matrix, not projection matrix, Gramian of this matrix, and then invert it, and then I will multiply itself, and then multiply itself transpose times this one. You may say that, but it sounds somewhat dumb to compute this ever-increasing sized matrix. So the idea is that let's reuse the previous result, the computed matrix, inverse matrix again, especially the matrix, inverse matrix again, and we recursively update our least squares problem. That's the idea of recursive least square. So, without loss of generality, suppose that we have this case. A0 is, for example, the A matrix obtained by using this first 50 observation. So the previous one. Okay. Now B0 is the vector obtained from this one. Anyway, we need some initial computation. So suppose we have this initial one. Now, we add one more line here. That is called A1. So A1 is A0 and one more line. That one more line is written as A1 transpose. As you see here, it's a row vector. So the authors named it A1 transpose. The convention in this textbook is that every vector is a column vector. So A1 transpose. Similarly, B1 can be written as B0 vector, and since we used one here, B1, now it's a scalar. So it's like you have added one more, actually one more equation, right? This times A1, this times A2 equals this one. The model function equals 0 says that. So it's nothing but we have partitioned our matrix A1 and our vector B1. And this is the convention, that these dots, actually even the research papers have that dots when they have partitioning of the matrix and vectors. Now, let's see what happens. So we want to compute the Gramian of A1. And what is A1? A0 and A1 transpose, and A0, A1 transpose. So it's an algebra now. A0 transpose A0. Good. That is the Gramian matrix from the previous step. Plus A1, A1 transpose. By the way, this is rank 1 update term. So our initial Gramian matrix has full rank. Then the next one has full rank. Now, the trouble is that we need to invert it. So we put this and hope to have this inverse plus some correction term. Then it would be great, right? How can you get some correction term that makes this equality? Actually, we've already seen it. Matrix inversion lemma or Sherman Morrison formula. In this case, this is rank 1. Now you remember the Sherman Morrison, how many R's and how many S's and how many N's. I'm not sure whether N, there are 2 N's or 1 N. 1 N, I guess. Right. And 2 R's. The Sherman Morrison formula is like this. You have an invertible matrix A and U V transpose. So you have rank 1 update. In this case, this is not U transpose, but you can set V equals U. And you may say that, wait a minute, this is not A. You can view this as A, right? By the way, do you still remember what is the inverse of this A plus UV transpose? I asked you to simplify and remember. So we regard entire thing as scalars. Then what happens? We may have some idea like this. A plus UV. Hey, what can I do? Let me divide by 1. A inverse UV. A inverse. Okay. So we have A inverse. And then we need to add and subtract. So here goes subtraction. So 1 plus. And in this scalar case, the order doesn't matter. But in this vector matrix case, order does matter. But I asked you to remember that this U appears as U, not U transpose. This V transpose appears as V transpose, not V. So since this is scalar, the only way to have a scalar is that you have A inverse and V transpose U. It's kind of quadratic form when V and U are the same. And then here you must have a matrix. So if you keep UV transpose, here you have A inverse and A inverse. This is Sherman-Morrison formula. So we apply this result to have this correction term. And interestingly, A1 Gramian of A1 inverse is the inverse of the Gramian of A1 is the inverse of the Gramian of A0 minus, let me copy, I do not remember the exact result. Yeah, here 1 plus A1 transpose A0 transpose A0 inverse A1 and A0 transpose A0 inverse A1 A1 transpose A0 transpose A0 inverse. So this is the result. Now, but we haven't yet finished it. We want to update our original X star 0. What is that? That is A0 transpose A0 inverse A0 transpose B0 to what? It seems that I have different notation, so let me use this as A0, X0. Now we update this to X1, that is the inverse of the Gramian of A1. Now, for this term, you can replace this one. Am I right? Now, for this part, what can we do? Again, A1 transpose B1 is what? A0, A1 transpose, and B0, B1 transpose. So, it is A0 transpose B0 that we already computed plus A1 A1 B1. So if in the previous step, if we have kept this inverse and this value, and then we can utilize again, right, this value, okay, to compute that one. So let me write it like this. So this is the update formula 1, and the second update formula is this one. Got it? So my current A1, B1 is my previous A0, B0 plus the correction term. And this is all from the current observation. So by plugging here, you have the complete formula for the update. By the way, our textbook made a change of variable like this as G0. So this becomes G1. So this becomes G0 inverse. But anyway, same thing. Okay? The authors probably didn't want to have this wide equation in their textbook, so they made a change of variable. By the way, even though it shows inverse, you never compute inverse. except the original A0 transpose A0 inverse. So the textbook also have that idea. Okay. Define this one as PK for the case PK plus 1, then this becomes PK. So actually they have something like this: PK plus 1 equals PK minus PK AK plus 1, AK plus 1 transpose PK, 1 plus AK plus 1 transpose PK, AK plus 1. Something like this. And for this one, xk plus 1 equals xk. And after some manipulation, you can show this. pk plus 1, ak plus 1, and bk plus 1 minus ak plus 1 transpose xk. Got it? I believe I'm correct. Yeah, you can do this. So after some manipulation, so how many terms? 1, 2, and 1, 2. So you have 4 terms. 4 terms here, but after some manipulation, this time this one becomes what? So sorry. This time this one becomes xk, right? So other 3 terms combined can be written this way. Here, the interesting thing is this part. So take a look at this update formula. It's an iterative algorithm form. My next movement, right? My next movement is the previous location plus a correction term. Now let's take a look at the correction term, especially this one. What is this? This is kind of, this is vector, so this is related to what I just told you in the noise canceller. What is this one? This is prediction of bk plus 1 based on the previous observations. Am I right? So this is what? This is prediction error. This corresponds to prediction error of bk plus 1. Actually, it should be yk plus 1, but we said b, so no problem. Got it? So the prediction error drives this update. If this is 0, then what do you have? This correction term is 0. So your xk becomes xk plus 1. This makes sense. You don't need to update. Now it's perfect, right? By the way, this form of iterative algorithm appears again and again and again in your estimation and detection theory course. Not again and again, actually twice. One for the Wiener filtering and the other for the Kalman filtering. Especially in the Kalman filtering, you will see something similar. By the way, we have another course because this 645 is titled as Statistical Signal Processing. Actually, it's estimation detection theory. By the way, the part of Kalman filtering and Wiener filtering is kind of taken out and has been served as a single course in control area. The course title is Estimation Theory, where you learn Kalman filter and Wiener filter throughout a semester. And there, this prediction error is called innovation. By the way, innovation means something new, right? So this prediction error contains new information. You cannot guess from the previous observation. So this new information drives your update. Anyway, it will be more clear when you take the estimation detection theory course. Okay, so let's see an example in the textbook. By the way, in this example of noise cancelling using second order auto-regressive model, you may say that, well, I can still invert the entire matrix because it's just 2 by 2 matrix inversion. But consider you have auto-regressive model of order 20 or something to have more and more accurate prediction. Now, what happens? Your Gramian matrix to be inverted is 20 by 20 or 40 by 40 matrix. Then, without this type of update formula, your computation may be too costly. By the way, some of you may ask like this. Initial starting point of P0, say, that may be also very computationally costly. You are right. So one of the cure is like this. Anyway, suppose it's noise cancel problem. You ignite, right, the engine. At that time, you choose P0 as identity matrix. Of course, it's absurd, right? It's just an arbitrary one. Now you start to update. If some time goes on, it will adapt. Got it? So this initial matrix inversion may not be a big problem in some applications. But anyway, since you have this initial P matrix, that is inverse matrix, then update formula can be easily give you the next guess given the new observation. Okay, let's see again this very simple case where this is line fitting again. So remember this problem, the first example? Where is this? This one. Right? Here you have 3 observations. So suppose you have 3 observations and you have found M and C. Now you have one more observation. Now you want to correct it. Now we have one more, something like that. And this example is again a simple case like this. So initially, your inverse matrix is this one, 1, 6, 3, minus 9, minus 29, A transpose B is 78, 22. So your initial guess of M, the slope, and C, the offset, is 6 and negative 32 over 3. Now suppose in your fourth observation, you have T3 is 5, Y3 is 18. Now let's update our guess of parameter. So this is exactly the initial ones. Now A1 transpose is 5, 1, because this is 5, and B1 is 18. It is appended here. Now, as we've seen in the previous derivation, okay, we just plug in. So P1 becomes the previous matrix minus a rank 1 term. Carefully see, this is just scalar, and what? This part is simply the first part transposed. So this is rank 1. Be careful. Even though this looks like some full rank minus rank 1. So your full rank may not be full lengthness or in invertibility may be ruined. Actually, it is not. As far as your observation is independent of previous observations. It is true when there is observation noise, random noise. So anyway, so you have update without doing any matrix inversion. So you plug this value here, and you plug A1, and here is innovation. And you got the updated value. And the authors also say that this is related to Kalman filtering, and you will see in EEC 645. Okay, so I believe I'm done with this linear least squares problem. By the way, according to our textbook, I believe this is fourth edition, right? We are almost finished the second part of the textbook. The first part was the preliminaries or review of the preliminary materials, and part 2 was the unconstrained optimization, and part 3 is linear programming, and part 4 is nonlinear constraint optimization. By the way, our next lecture note will be about some randomized search method. Originally, that was the next chapter to this one. So that's why we cover not following the original order of the our lecture note. So let me see. Is this? Yeah, this is chapter 13, right? Correct. Okay. So we have randomized such method to be covered next week.